カリのポタトリカニマロマニカロチカババババナナ
Oh, despicable me.
In the video before this one, we started talking about Venn diagrams, sort of what they are and how they represent data visually. So in this video, I'm going to share with you a method that I use with students when I tutored finite mathematics. And this is a way to make solving Venn diagram problems very concrete. So we're going to develop this method so whatever is thrown at you, you can actually do it step by step in a very logical, systematic manner, and that will allow you, of course, to get the correct answer. So let's go ahead and take a look at it. Now, what about this Venn diagram region method? So it starts with a couple of basic ideas. Remember that any Venn diagram can be broken down into several discrete regions, and I'll show you that here in a second. Now, each set, subset, intersection, or union, etc., can then be written as a list of whatever regions comprise that. So we might have a union of a couple sets, and we can make a list of all the regions that make up that union. Now, from those lists, you can then figure out intersections. You can figure out other unions, or whatever the problem might ask you to find. And of course, once you have sort of your list-based answer, you can then go back and shade in the appropriate regions in the Venn diagram itself. Again, this will all make sense when we do the examples here in a second. Now, just one caveat. When you make a Venn diagram and you list the regions on it, it's a good practice to label that Venn diagram as U sub R or S sub R, so universal set of regions or sort of the set of regions. That's what the sub R means. That way you don't confuse the region labels with the actual numbers that are part of the problem. So you might label region, the intersection as region 1, but the problem may have a 3 in that region because that's the number of elements in that region. So you want to be very careful when you're labeling your regions in your Venn diagram to keep the region labels separate from the element numbers in the problem. Okay, so let's take a look at this. So here we have a Venn diagram, of course, and we have two sets. They overlap, so they intersect. They're in the middle. And what I've done is I've gone ahead and split up the Venn diagram into discrete regions. So the intersection there in the middle is region 1. Over on the left, everything that's just in A, that's region 2. Everything that's just in B is region 3. And everything outside of A and B is region 4. So we can ask some questions. Which regions make up A? Which regions make up B? Which regions make up A intersect B? And which regions make up A union B? So we'll tackle all these in the next few slides. Let's talk about which regions make up A. And this is actually pretty simple. Regions 2 and region 1, those make up all of A, all of the circle, all of the set of A. So we can go ahead and shade that in like that. And see, that's how this works. This is obviously a very simple example, but it helps us solve much more complex problems. Which regions make up B? Well, that's 3 and 1, or 1 and 3. So we can shade it in like that. Which regions make up A intersect B? Well, if you know anything about intersections, you know that that is region 1 there in the middle. So we can shade it like that. Which regions make up A union B? Well, we know the union is anything that's an A, B, or both. So it's regions 1, 2, and 3. And we can shade it like that. So you see how this works? All we're doing is we're making a list of regions that comprise whatever we're asked. So here we're asked A union B. we go, hey, well, that's regions 1, 2, and 3. Then we can go back and shade that in. Now let's take a look at sort of a different set of questions we can ask about this data and, of course, then answer. So oftentimes you're asked to find the opposite or the complement of some region or set, intersection, etc. So now we are asked which regions make up a complement, or which regions make up the area that's not A. So if A is made up of regions 1 and 2, then not A has to be everything else, which are regions 3 and 4. We can go ahead and shade those in. And this diagram should make sense. So A is regions 1 and 2. Of course, that's not shaded. That's not what we're looking for. We're looking for everything outside of A. So A complement. And that is regions 3 and 4. We can go ahead and shade that in. Which regions make up B complement? Well, if B is made up of regions 1 and 3, then B has to be, the not B has to be.
In this video, I'm going to talk about permutations and combinations. And I'm going to use these little red, green, and blue squares. I'm going to calculate the permutations for 7 objects, between 1 and 7 objects. And I'm going to show you the official equation. It looks kind of nasty, but I will walk you through it. Imagine I have 3 squares, red, green, and blue. And for a combination, the order does not matter. If I have a green, blue, red square combination, a red, green, blue square combination, it's still only one combination. For permutations, the order does matter. I can take these 3 squares and make 6 permutations. Now let me just fill in all the squares and all the different permutations, and I will have 6 hopefully. There's 1, 2, 3, 4, 5, 6 permutations without repeating. And only one combination. So we have 6 permutations and 1 combination possibility. So now imagine I have 4 squares instead of 3. I still can only make 1 combination from those 4 squares, but I can make 24 permutations. I can rearrange them 24 different ways for 24 permutations, but I still only have 1 combination. I am going to show you the permutations of different number of objects. I'm going to start with 1 and end up with 7. So with 1 object, it should be pretty obvious. There's 1 permutation. Now with 2 objects, I have a red and a green object, and I can sequence them 2 different ways, or order them 2 different ways, and that gives me 2 permutations. So I take 2 times 1, and this is equal to 2. With 3 objects, I have a red, green, and blue. So I have 3, which is n. 3 is n. 3 times 2 times 1, which gives me 6 permutations. Now I have 4 objects, so n is equal to 4. So I have 4 times 3 times 2 times 1, like that, which equals to 24 permutations. Now I have 5 objects, or n is equal to 5. And I take 5 times, you guessed it, 5 times 4 times 3 times 2 times 1. And this is equal to 120. And now I'll imagine I have 6 objects. And you probably understand now it's going to be 6 times 5 times 4 times 3 times 2 times 1. And this is equal to 720 permutations. Now with 7 objects, this is my last one, I have 7 times 6 times 5 times 4 times 3 times 2 times 1, and that equals 5,040. And it turns out I can take these 7 objects and create 5,040 different permutations. You probably notice the same pattern, the 7 times 6 times 5, and then 6 times 4 times 3 times 2 times 1, and so on and so forth. I can't read that fast. And then I have 4 times 3 times 2 times 1, and so on and so forth I go. There's a word for this, and a symbol too. It's called factorial. So the shorthand notation for 2 times 1 is 2 factorial. The shorthand notation for 3 times 2 times 1 is 3 factorial. You're probably guessing this one's 4 factorial. And 5 times 4 times 3 times 2 times 1 is equal to 5 factorial. Again, this is shorthand notation, so you don't have to write this out every single time. And the last one, of course, is 7 factorial. So you might even see it written like this in your textbooks, or your professor does it this way. The only thing the factorial symbol means is, like in this case, 3 times 2 times 1 is 3 factorial, and 2 factorial is 2 times 1, and so on and so forth. Also, 1 factorial is 1. Now, if I want to know the number of permutations, I just take the number of objects I have, factorial, and this is my permutations. So if I want to know how many different ways can I organize these 4 objects, it's 4 factorial, which is simply 24. Now, the official formula is this: n factorial divided by n minus the small n factorial. In other words, how many different ways can I organize these 5 objects? Take an n at a time, the number selected. In this case it's 5, I'm taking all 5. And this is equal to 5 factorial divided by 5 minus n, which is 5. I'm taking all 5 of these objects and all this factorial. This is equal to 5 factorial divided by 0 factorial, which is a new idea maybe for you. And it turns out 0 factorial is equal to 1. But so is 1 factorial is equal to 1. It's one of the mysteries of math, and I'll maybe discuss that in another video. I will discuss that. So now I have 5 times 4 times 3 times 2 times 1 divided by 1, which is equal to 120. So it turns out that I have 120 permutations and 1 combination. And 120 permutations. I'm probably repeating myself. In the next video, I'm going to talk about how to calculate permutations and combinations if I have 5 objects. And let's just say, for example, I pick 3 at a time. I pick those 3, or those 3, or these 3, or maybe some in the middle, like the green one, the yellow one, the purple one. And I'll use 2 different equations. And this is equation again for permutations, and this is equation for combinations. Notice I just add that one little thing. Again, I'll discuss this in detail in the next video, and see you there.
Hello, this is David Harper of the Bionic Turtle with a brief tutorial on combinations and permutations. This is a basic part of probability theory that we use to help us count or enumerate all of the different possible outcomes. To show you, I'll give you an example. Let's assume that we're hosting a dinner party and we invite 5 dinner guests. It's a diverse crowd, including Superman, a magician, an artist, a policewoman, and a librarian. But let's also assume we're not the greatest host ever, and we only have 3 chairs or seats at the dinner table. So we can first ask a permutation question, and that is, how many different ways can we seat 3 people at the table if we do care about the sequence or order? So permutation is denoted this way with 2 subscripts, notice that, N and R, P for permutation, and that means it's the arrangement of N objects taken R at a time. In this case we have 5 people, so it's 5 objects, and we want to seat them at the table 3 at a time, so R equals 3. The key word in this is the arrangement, because a permutation does care about the sequence or the order of the objects that we draw R at a time. So for example, if we seat at the table the artist, the magician, and Superman, that right here is a permutation. Now, if we take that same group of 3, that excludes the librarian and the policewoman, but the order is different in this way, Superman, the artist, and the magician, see how that's the same people but a different order? Well, that does count as a second and a distinct permutation. So that's the thing about permutations. The formula's here. It's given by this function here, n factorial divided by n minus r factorial. In this case, that would be n equals 5, because we have 5 people we invited to the dinner, divided by 5 minus r. R is 3 because we want to take 3 people at a time seated at the table. Now, combinations are similar, but a combination does not care about the sequence of the order. So it is given also here denoted with 2 subscripts, N and R, but a C instead of a P, C for combination. It's a selection of N objects taken R at a time. Notice instead of arrangement, we're saying it's a selection because we do not care about the sequence or the order. So if we take that same group, the artist, the magician, and Superman, and if the order changes, it's the same combination. It does not count as a separate combination. So you can see we're always going to have fewer combinations than permutations. And in this case, the combination is given by n factorial divided by r factorial multiplied by the quantity n minus r factorial. And here is a shorthand notation for the combination n over r. In this case, you can see at the bottom, the answer turns out to be only 10 because we have a larger denominator. So we can try an example here. Given a set of 7 letters, A, B, C, D, E, F, G, we can ask how many permutations of 3 letters and how many combinations of 3 letters. For permutations, this is the formula, and the answer would be 7 factorial, because we have 7 letters, divided by 7 minus 3, because we're taking 3 letters, we're drawing 3 letters, and so that's 5040 divided by 24, or 210 permutations of 3 letters out of a set of 7, 210, and that's where, remember, sequence or order does matter. We called permutations. That's about the arrangement. Now for a combination of 3 letters, that's going to be a lower number. We have this formula here, so notice the difference is really, it's a permutation, but we add this 3 factorial in here because we're taking 3 letters. And so that turns out to be 210 divided by 3 factorial, or 35 combinations of 3 letters, as opposed to 210 permutations, because there are several duplicates of combinations where the letters are the same but the order have changed. Okay, so let me just show you how to do that in Excel real quick. Here I am in Excel, and first let's ask, if there are 10 people, how many different ways can we arrange or seat them at a table for 4? So this is going to be a permutation because we do care about the arrangement. And so n is 10, r is 4. Here's the formula for that permutation. And Excel, as it oftentimes does, has a built-in function for us equals PERMUT open parens. I take the number, in that case that's n, how many total objects? Well, in this case we have 10 people. Those are the objects. And we want to sit 4 at a time at the table, so comma 4. That's the permutation formula right there, very simple. We get 5040. Now let me do one more example. What about a poker hand? I should say 5-card draw. Let me just say 5-card draw poker hand. So that would be a poker hand where we hold 5 cards in our hand, but we don't care about the order. In that case, that's a combination question because it's a selection. We're not caring about the arrangement. N equals 52 because we have 52 cards. R equals 5 because we're taking 5 at a time. Here's the formula for the combination. Here's that shorthand notation you'll recall. And as usual, Excel has a built-in function for us equals COMBIN, and it takes the same parameters as permutation. 52 cards in the deck, comma, we're drawing 5 at a time. We're doing combination because we don't care about the sequence. And it turns out, I'll put a comma there, there are 2,598,960 combinations of 5-card selections for a 5-card draw poker hand. So that's combinations and permutations in a nutshell. Thank you for your time.